Hello, good morning, good afternoon, or even good evening to everybody. It is a pleasure to have you back for this new Analyze Thursday webinar about data center. After a first webinar in June, we are running here a second season to discuss about data center with a new angle. To do so, I will be joining in a few minutes by the expert and especially with Eric Mounier, Director of Market Research. He will be your host today. And he will be joining also by Thibaut Rossi for the memory inputs, Hassan Chaito for the power electronic part, and Ta Ayari presenting his insight in compound semiconductor. I think we are ready to go now. Eric, the floor is yours.
Okay, so welcome everyone. I'm Eric, I'm Chief Analyst at Yole Intelligence, and I will be your host for today's event. So today's event will continue the series of Analyst First Day events focused on the hot topic of data center. Indeed, the growing demand for increased workload in various data center applications, such as cloud computing, large language models, or generative AI, necessitate faster and more powerful processing, higher memory capacity, and of course, enhanced bandwidth and networking capabilities. This change will inevitably lead to a surge in data center power consumptions. So, lowering energy consumption per byte of data is thus a significant challenge for data center today to address these overall power consumptions. Therefore, today, following your initial webinar on processing and memory in data center, we'll focus on three other critical topics that are CXL, photonics, and PSU. These three technologies will shape the future of data center architecture, with CXL enhanced performance, photonics expanding bandwidth, and of course PSU optimizing power. My first talk will provide an overview of the current data center industry, covering the different types of server, the technological trends, market forecast for server. We will, of course, also examine how the data explosion is evolving into a technological revolution to meet the growing demand for data at a lower cost and, of course, reduce power consumptions. So, as you can see on this graph, the total amount of data that will be created, captured, or copied and consumed globally will reach 181 zettabyte 10 to the power 21 in 2025. In 2020, the growth was quicker, caused by the increasing demand due to the COVID-19 pandemic, as of course, more people work and learn from home and use home entertainment. What are the data center drivers? There are many of them. The first is the revolution of artificial intelligence that will require much more powerful processor, GPU, CPU, and of course, much more storage server. Crypto mining is another big trend that will require more powerful computing. E-commerce expansion. We estimate that in 2023, the US e-commerce sales will exceed 1.1 trillion, up to 10% increase year over year. And of course, to support this growth worldwide, the data center infrastructure will become a must to handle online retail operation, manage customer data, and of course, ensure seamless shopping experience. Digital transformation, administrative transactions as in private as well in public sector are switching to online platform and are targeting paperless, saving time and reducing carbon footprint by reducing mobility. One very strong driver is video streaming. Because of the popularity of video streaming platform has increased, requiring for new data center capable of delivering high bandwidth and of course low latency performance. Home office revolution. Following the COVID-19 pandemic, remote work and virtual collaboration tools have increased the reliance on data center for hosting video conferencing, Teams meeting, and of course remote solution. Social media influence. Data center will manage enormous amount of user-generated content, interaction, and real-time data analysis. And the last one, 5G and IoT, that require vast amount of data for more and more connected devices. All these drivers will change dramatically the infrastructure of data centers. So when we talk about data center, we have to distinguish between different types of data center. To make it short, there are three types of data center: enterprise, HPC, and hyperscale, which are defined by the estimated number of servers, also the power consumption, and of course, the organizational use. For example, enterprise data center, which are facility owned and operated by a single organization, is 1 to 10K servers, and its main purpose is for internal IT services. HPC is a facility that provides very complex computational tasks with very powerful processing. It's usually owned by government, academic, or research institute, and servers are limited accesses. Nevertheless, it can be quite big data center up to 10K nodes. Just to specify that in case of HPC, we will rather talk about nodes than server. And the last one are hyperscaler. It's usually the GAFAM, Microsoft, IBM, Google, and so on. That's a huge number of servers, 5K to 500K, and their main usage is for cloud services. Another way of showing the trend is to see will it be used for cloud or edge. Actually, the frontier is becoming blurred because so far, enterprise and hyperscale were mostly using cloud services, while HPC were mostly used edge services. But for example, for HPC, some projects are moving to cloud for specific tasks, and for hyperscale, some projects will move to edge in specific geographical area to decrease latency. So compared to the trend a few years ago that what 80% the cloud, 20% the edge, we see a move to 20% the cloud, 80% in the edge. The advantage of the edge is, of course, to offer reduced latency, better security, and compliance. On the other hand, cloud, with a centralized facility, usually far away from user, provide a wide range of computing resources, storage to users all over the world. So let's examine what is the rack, and it is the main topic of today's webinar. So into a rack, there are many different servers, compute server that will manage the resources, storage server that store, retrieve, distribute, and backup or archive computer data application, networking server, basically we call it switches that will be the network connection in the data center for receive, processing, and routing data from one destination to another. We call interconnection, basically optical transceiver, but also I/O, such as optical I/O, or in the future, co-packaged optics. And we call also many parts dedicated to power, such as power supply unit or PSU, power distribution unit, PDU, battery backup, and cooling. Cooling can be done either by air, liquid, or immersions. So, as you can see on the graph, there is a big growth of the number of hyperscale data centers in the world. In 2025, we estimate that more than 1,000 hyperscale will be in operation worldwide. And compared to the total number of data centers in 2022, the hyperscaler is already 13%, and this number will grow over the next years. The four leaders of the infrastructure are well known. They are Amazon, Microsoft, Google, and IBM. Each of these companies has more than 60 data center locations. If we look at the geographical location, US and China account for more than 60% of worldwide hyperscale data center. And other popular countries are Japan, Germany, UK, Australia, and Canada. These two forecasts in terms of number of servers, so you can see that it will go for a bit less than 23 million units in 2023 to 29 million units in 2029. And despite the decrease in 2023, the server dedicated to artificial intelligence will still have increasing share. So if the total number of servers has decreased this year, the relative part of AI server has still increased. And in value, so the graph show here the market value for server forecast for computing, storage, and networking. It will grow for almost 140 billion in 2023 to more than 240 billion in 2029, with an impressive 10% CAGR. And computing server market will have the largest growth due to increasing price for AI server. At Yole, we deeply look at what's going on at the semiconductor and chip level in server. So this is our forecast for the semiconductor server value in US dollar billion over the next 5 years. So actually, today, the market value for semiconductor in server, including memory, processor, optical interconnect, and so on, is close to 70 billion of US dollar, and it will grow to more than 230 billion in 2029 with an impressive 90% CAGR. We estimate that in 2029, the semiconductor in the server will represent between 25 and 30% of the total semiconductor worldwide. So quite a significant value. So this is what I show here. Today, the total semiconductor device is in the range of 544 billion US dollar, and the server device in 2023 will be more than 70 billion US dollar, accounting for 13%. In 2029, this will jump to almost 30%. So big change in market means big change in technology, because we're moving from data explosion to technology explosions. So many applications such as crypto mining, e-commerce, video streaming, home office, and so on, which require more memory, lower latency, lower cost, more bandwidth, lower power consumption, more processing power, that will increase change in computing, memory, storage, and networking power application. And at the chip level, we see many changing, what I call a technology explosion at the level of computing with quantum computing or photonic processing or neuromorphing, at the interconnect with SmartNIC or CXL, at the packaging level for HBM 2.5D, or new architecture with disaggregation, or the use of non-x85 architecture. So if we look at this different technology, of course, they don't have the same level of maturity. Some of them are quite far from technology maturity, such as quantum computing or neuromorphic or optical computing or optical I/O. But some of them are already implemented, such as chiplet, HBM, advanced packaging, or SmartNIC. So to conclude, we are entering a data explosion era driven by increasing demanding workload and the need for faster data processing, higher memory capacity, and bandwidth. This data explosion turned into numerous technological innovation, and today we present three of them: CXL technology, photonics, and power. And all the data presented today are extracted from a future report to come that will be semiconductor trained data center that will be released in January 2024. So I will now pass to Thibault, which is Senior Technology and Market Analyst in Memory, that will now share insight on CXL. And although still in early stage, the technology is gaining momentum, increasing support for resource optimization, and of course, accelerating data center workload in the future. So Thibault, the floor is yours.
Thank you, Eric. So now I'm going to briefly present you some extract from the Memory Processor Interface 2023 report, which is focusing on CXL. As you are probably aware, data centers are facing and will be facing a fair amount of challenges. Among them, clearly, the memory bottleneck is the one that make most of the rationale for the CXL adoption. So here's an overview of the different memory challenges and bottleneck in the data center. So first, we have the memory bandwidth per core, which is decreasing. So since 2012, the average number of core per server has increased by a factor of 3. And clearly, the memory did not scale as fast as this. So this results in memory bandwidth per core, which is actually decreasing. Second, we have the memory hierarchy that probably needs further optimizations. There is a pretty big latency and capacity gap that still exists between the last layer of memory and the storage devices. And we believe CXL could actually help filling that gap. Third, there is the cost of memory per server, which is increasing. If you look back in 2015, the DRAM was representing about 15% of the server ISP. In 2022, we are now reaching almost 30%, and we expect this to reach almost 40% by 2025. Another challenge in the data centers with memory is the memory stranding. Memory stranding is a pretty common issue in current server architectures. It happens when the cores are all fully allocated to tasks or virtual machines, but some of the memory remain unrented. And clearly, this is leading to a situation where there is an inefficient use of the memory resources. And last point, this is about the workload which are growing in complexity. Here we're thinking mainly about HPC and AI and machine learning servers, which are running over larger and larger models and that are very memory capacity sensitive. If we take the example of the natural language processing, NPC models, the numbers of parameters has increased by 14 per year. So you have to keep in mind that the memory has to grow as fast as the model almost. So there's a pretty big demand rise there. So now let's have a look at what is CXL and what is it for. So first, what we have to have in mind is that there is a clear shift towards heterogeneous computing. So while homogeneous computing simply rely on the CPU and associated resources around it, heterogeneous computing is using multiple types of processing device. So it's still using the CPU, but it also add to this, accelerators such as DPUs, GPUs, ASICs, or FPGA. All those processing units can work in parallel to accelerate the computation speed in high data intensive applications. Clearly here we have in mind AI and machine learning, for instance, but potentially as well HPC. So CXL is an open standard for high-speed CPU to device, CPU to memory, and device to device interconnect. And it has been designed to accelerate the execution of next generation of data center workloads and get the full potential of the heterogeneous computing architecture. CXL, which actually run over PCI Express physical and electrical layers with protocols covering three main areas. First, there is the IOs, then the memory, and third, the cache coherency. So now, if we look at the different type of devices which are using those CXL protocols. So through the combination of those three protocols, so here referred as CXL.io, CXL.cache, and CXL.mem, three use cases are possible. The first one is type 1 devices, which are actually using CXL.io and CXL.cache. Here we're talking about accelerators without attached memory that may require to have access to the processor attached memory. And here we have in mind accelerators such as NIC, for instance. Type 2 devices are devices that can currently access to the host memory and allow the host to access to its memory. So the typical example here are going to be accelerator with attached memory and optional coherent cache. We have in mind here like FPGA, ASICs, and GPUs. And finally, the main area of interest to us, type 3 devices, which use CXL.io and CXL.mem protocols, so those devices allow the host to access and manage attached memory devices. So here we're thinking clearly about memory buffer or memory expanders, okay, that will allow the host to expand access to additional memory for capacity or bandwidth expansion. And this is typically the main focus of the report, those slides I extract from. So now let's have a look at the different CXL revision and what they actually mean in terms of memory expander use cases. So first, we have the CXL 1.1. And here we're talking about in-server memory expansion. Purely at server level, using the PCI Express lanes, we'll be able to add CXL memory expanders to help increasing either the capacity or the bandwidth of the memory. Then we have CXL2, which is going to enable CXL switches, allowing the configuration of memory pools. So here we're going to have a few CXL memory expanders via a switch that would be accessible by few hosts here, and I mean actually few servers. And here we start to get configurations where the memory is becoming shareable among different servers, and therefore a better an optimization of the memory resources usage. With CXL 2.0 running over PCI Express 6, okay, which is actually doubling the bandwidth versus PCI Express 5 or CXL 2. With this, we will start to be able to cascade CXL switches, which is going to enable the server full disaggregation and composability. And this of all the resources, and this is inclusive of memory. So just to make it brief, every pool of resources would be under a switch. Yeah, so, and then on top of it, we would have Fabric Manager managing and composing the different virtual servers. So another area of interest with the CXL 3.0 is the fact that we will be able to have device-to-device accessing each other. And in that case, we could think of having CPU and CPU, GPU, and GPU having directly access to the memory pool without having to go through the CPU host. Now, coming back about the different additional layers the CXL is gonna provide. So you have to remember that between the DRAM and the NVMe SSDs in the memory hierarchy, there is a quite substantial gap in terms of latency, since we're talking about a factor of 1,000. Clearly, CXL presents an opportunity to bridge this gap by introducing far memory and subsequently allowing for the inclusion of additional layers in the memory hierarchy. These layers can be classified into 3 levels, each offering a distinct level of latency and bandwidth. So first, we have the direct attach CXL memory expanders. Then we're going to add pooling for using DRAM-based expanders. And finally, the memory pooling, which are going to use emerging non-volatile memory solutions or NAND flash. With these 3 layers, we'll be able to use various types of memory devices, and we categorize them as this. So first, we have the CXL memory expanders, which are DRAM-based. Secondly, we're going to add the persistent memory, and here we have in mind solutions such as 3DX Point, MRAM, or NVDIMM, for instance. And third, the storage class memory, such as the CXL SSDs. Now, if we look at all those type of devices, clearly the CXL memory expanders, DRAM-based, are expected to represent most of the near-term demand. These are available in 2 form factors. First, there is the add-in cards, or also called AIC later on, and these include a CXL memory expander controller, but need to be populated with traditional DRAM DIMM. On the other side, there is also the drives using the E3.S form factor, which are actually fully integrated solution in which you will find the DRAM chips, the DRAM chipset like PMIC, required for DDR5, as well as the CXL memory expander controller. So now let's have a look at the roadmap of memory expander type and use cases. So first, let's be clear, the CXL adoption rate is going to be detected by the availability of CXL capable server CPUs. Currently, only CXL 1.1 capable server CPU are available, and we expect CXL 2.0 CPU to reach the market by 2024, and CXL 3.0 CPU by 2025 and 2026. Looking at the memory expanded types, on the short term, AIC expected to represent most of the demands, but quickly drives 8 lanes PCI Express configurations are expected to take over. And this is mainly because they are more optimized and standard form factors in data centers. With CXL 3.0 and the transition to PCI Express 6, which doubled the bandwidth compared to PCI Express 5, we may wonder if CXL 4-lanes drive could emerge for capacity expansions use cases, for instance, but this is more question mark there. Considering the use cases, until CXL 2.0 CPU, until the CXL 2.0 CPU are released, the use cases are going to be limited to direct attached memory expander, so in the server itself. Starting with CXL 2.0, we'll start to see the rise of memory pooling behind a switch. Okay, so having the memory share across different servers. And with CXL 3.0, we may start to see also the emergence of multi-headed memory pooling devices. So just to give an idea, compared to the pooling behind switch, multi-headed devices offer lower latency, but will be shareable with a more limited amount of servers. And they will clearly require a more complex wiring. So here's an overview of the CXL adoption expected milestones. So this is an estimated timeline. So clearly, at Shure, we believe that CXL has the potential to revolutionize memory utilization and access, leading to widespread players. For instance, AI servers are expected to see a clear benefit starting CXL 1.1, mainly for inference at the beginning. But we expect to see an increasing interest starting CXL 3.0 and the possibility for GPUs to have directly access to a pool of memories. For HPC servers, cloud, and hyperscalers, if there might be some interest at starting CXL 1.1, we expect to see some more traction starting CXL 2.0 and the possibility to share memory resources with memory pool use cases. But especially for hyperscaler and cloud providers, we expect to see a strong acceleration with the emergence of CXL 3.0, mainly for the possibility that this offer regarding the full server disaggregation and composability. That can be a way to combine resources in a very efficient manner. Looking at in-memory database and analytics, we believe they could see interest for all the clearly depend on the actual gain in performance versus the additional cost for each of these configurations. So overall, we believe that CXL will also bring, new hardware, new software, and new complex systems that will clearly enable a totally new market, if not an entire new industry in the coming years. Some numbers to finish. If we look at the DRAM expanders, we expect the market to reach 15 billion by 2028. If on the short term, we expect add-in cards form factor to represent most of the volumes market. By 2028, we expect the drive to represent almost 90% of the market. Now, looking at the use cases, currently the direct attached memory expansion is the only use case possible. But in the future, we expect memory pooling to represent most of the market. And just to make it clear, we expect direct attached memory expansion to remain, but mainly for bandwidth purpose, while the memory pooling would be there to also address the capacity expansion mainly. More looking at the overview, this last slide about the markets. I already mentioned about the CXL memory expander revenue of 15 billion by 2028. So most of it is going to be composed of DRAM revenue with 12.5 billion, and almost 600 million will be for CXL memory expander controllers. Side of it, there is also the market for CXL switches. Here we're talking about only the switch itself. We expect this market to reach 741 million by 2028. And this ends my presentation about CXL. Thank you. Eric, I give you back the floor.
Thank you, Thibaut. So CXL is expected to quickly gain stronger adoption in the industry indeed. But when we talk about increasing data bandwidth at high speed, photonics technology naturally comes to my mind, at last to my mind, because photonics will undoubtedly play a crucial role in data center from very short distances, such as optical I/O, to optical transceiver for short and medium ranges, as well as new architectural solutions like CPO. So I will continue by presenting some insight on that. Actually, there are many changes in the data center architecture. So if we map all the different technical changes for optical interconnection over the next 5 years, we see that many of them are concerning optical technology. So I invite you to look at what's going on at the bottom right, that is the part dedicated to metro access for cloud and DC interconnect. You can see that on this part dedicated to data center network, silicon photonics, for example, will penetrate more and more into intra-data center interconnect with, of course, new type of material for higher speed and low power consumption modulations. Current technology coming from the telecom field will also penetrate data center interconnect. Co-packaged optics, which has been development over the past year, might become commercially available soon. And also silicon photonic, a very interesting technology taking leverage of CMOS and wafer scale manufacturing, will get increasingly market share at every level of the data center interconnect, from optical I/O to pluggable to co-packaged optics. So why using photonics in data center? There are 4 main motivations: high speed, AI, machine learning application, low cost, and low power consumption. If we look at high speed, there's current commercial development of 100G in volume, and 1.6 tera has been announced by several vendors. Also, the switch ASIC throughput will increase to 51.2 terabits per second, and 102.4 terabits per second is expected in 2025. For AI and ML application, we see more and more use of generative AI, automated logistic manufacturing application, autonomous driving for cars, and future healthcare that will also require increased bandwidth, lower latency, and more processing power. Low cost is very important in data center, that we need to choose the right technology for each application. Because it's a high volume market, it's very important to have high volume module adoption for the operator to carefully choose the right technology. And the last changes, which is very important, is the low power consumption. And we see more and more new technology coming to decrease at every step the power consumption of the server using new technology and new device. Just to name a few, we use new type of modulation, low power electro-optical modulation. We remove DSP to use linear drive optics. We use more efficient laser with better coupling. We avoid gearbox to match SerDes and optical lambda speed. And also, we try to have a deeper integration with, for example, co-packaging of optical NG and switch ASIC. Actually, it's important to see that optical transceiver and photonic in general are fundamental links in the data center, You can see that they are used for routers that used to direct internet traffic and to select the good path for traffic. Transceiver are also used for switching, for network switches that are used to connect different devices on network. That, of course, used for server, the specialized computer that will deliver data to internet. And of course, all data center contain server, could be computing server or storage. And also, they are connected to NIC and CNA card. These cards are used to connect computer to the internet. And we see that as we move over the time, copper is step-by-step replaced by optics. So in current network, most links within the rack are copper. But as the data rate increases, the longest copper links will need to move to optical. As you can see on this graph, in the 80s, all the interconnect in data center for data center interconnect, metro, and of course within the system was copper cable. And over the year, step by step, as we get closer to the chip within the system, we move step by step to optics. Today, optics is used up to DC inter-rack, I mean 3 meter to 50 meter distance. As we move closer to the chip, there are currently development for chip-to-chip, chip-to-module, and board-to-board development, replacing copper by optics, using, for example, integrated optics, embedded optics, and silicon photonics. What is the situation of migration today to move to higher speed optics? For intra-rack, I mean quite short distance, 1 centimeter to 50 meter, most of the interconnect are copper. But we move step by step to optical I/O, and silicon photonics will be necessary technology to integrate optical I/O for inter-rack. Inter-rack interconnection is 50 to 100 meter length using either active optical cable or internet interconnect, are today using 100G, 200G, up to 100G, and we will still more and more move to 400G and 100G in the future. And then when we go to larger distance, intra-data center, I mean from 100 meters to 80 kilometers, then we will see the use of co-packaged optics for 500 meters to 2 kilometers. And this is where, for example, we will have advanced packaging technology to merge switch ASIC with pluggable. Today, this is mostly also the silicon photonic domain, at least up to 2 kilometer distance for 1G, 100G, 200G, 400G DAR, 100G. Then, if we continue investigating what's going on for silicon photonic, actually silicon photonic peak can be used at different levels. For optical I/O, the shortest distance in data center, pluggable, they have been implemented into pluggable since a few years now with players like Intel or Cisco, for example, and co-packaged optics, the merging of switch ASIC with pluggable. You can see on the right, you have the basic structure of a data center with the rack, the top of the rack, and the different switch level, the leaf, the spin, and the core. At the top of that, you got the data center interconnect. And you can see that almost at every level, silicon photonics can be used. What is really new today is interconnect server to server, which is really the domain of silicon photonics technology for optical I/O. If we move to the switch level for top of the rack and leaf spin switch level, this is also a domain where silicon photonics could be used for co-packaged optics. CPO has been delayed for volume development, but it's continue in R&D, and we are quite optimistic that in 2028, we will see the first volume development of CPU. And for the interconnect among data center, we talk here about 80 kilometers up to 120 kilometers. There is also a domain of silicon photonic technology with technology coming from the telecom, I mean current technology. Here, only one company, which is Acacia, which is part of Cisco, is currently developing and selling this current technology using silicon photonic platform. So in terms of market growth, if we compare Datacom to telecom, we can see that actually Datacom optical transceiver for Datacom will have the highest growth from 2022 to 2028, growing from 6.3 billion in 2022 to 14.8 billion, almost 15 billion US dollar in 2028, with a 15% growth rate. Now, if we look also at different type of optical transceiver, or I mean of application, today integrated optics is not so much used. It's quite a small volume, $38 million, but we forecast by in 2028, due to the use of co-package and more use of integrated optics, this market will be close to $140 million US. Integrated optics, Internet pluggable and active optical cable, which are also pluggable, will grow from $6 billion US to $14 billion US in 2028. If we look at the optical transceiver market for Datacom, so actually the optical transceiver market for Datacom is expected to grow from 6.3 billion in 2022 to 14.8 billion in 2028. And this growth is coming from increasing demand driven by AI, machine learning application, increasing video streaming and data transmissions. And of course, at the same time, all the service providers are trying to decrease the total cost of ownership for the network, I mean the US dollar value by gigabyte. In terms of shipment, the shipment Datacom will grow from 75 million units in 2022 to more than 1 million units in 2027. And the vast volume of the optical transceiver for data center will depend on the investment plan and demand coming from hyperscaler in the USA and China. We believe that the high demand will continue because we continue building new data center to enable high bandwidth with lower latency, and also due to the rapid rise of internet traffic due to streaming video and the emergence of new applications such as AR/VR, connected car, automated logistics, manufacturing, that will accelerate the deployment of optical module. So to conclude this snapshot on photonic for data center, so the demand for capacity is driven by the growing need of very large cloud services provider and the emerging of new applications such as generative AI, frontier models that will accelerate the deployment of new photonic modules. Optical interconnect will become essential technology in telecommunication infrastructures, and the development of semiconductor technologies such as laser modulation and DSP enable an increase in bandwidth and accelerated the data rate of the overall infrastructures. The total revenue will still increase significantly despite the local pandemic measure in China last year. But the recent shift to the work from home and study from home approach, which was driven by the COVID-19 pandemic, will continue and will reflect the traffic increase and thus the demand from data center operator to accelerate the development. And at the technological level, integrated photonics and PICs will hold great promise for realizing low-cost and scale optical solution, not only for communication sensor sector, but as optical links are moving to higher transmission while switching to shorter range, the optical technology is poised to be at the forefront of short-reach interconnect. And the leading candidate of the evolution in terms of technology will be silicon photonics. So I hope I demonstrate that photonic will be enabling technology that will offer greater capacity and new architecture options for data center. However, the pursuit of more efficient data center comes at a price in terms of energy consumptions. So there is continuous technological innovation to enhance data center energy efficiency and operations. So the next speaker will be Hassan, experienced analyst in power and TAA, technology and market analyst in combustion reactor, who will discuss the major trend in data center infrastructure and PSU to support the demand for more powerful server. Just to conclude, all the data presented for photonics are extracted from 3 reports we have on silicon photonics, CPO, and optical transceiver. Thank you. So, Hassan and TAA, the floor is yours.
Thanks, Eric, for this introduction. So in this last section, we are going to talk about the Power Electronics for Data Center 2023, which is a report which has been released earlier last month. So why we are speaking about the power and data center application, only about software, memories, or CXL topics with servers, GPUs, and stuff, and how much a data center can consume. So as we can see, a large data or hyperscale data center can consume up to 100 megawatt, and total consumption of the all data center worldwide are effectively 2% of the total produced electricity, which is far than being negligible. For instance, the total consumption of the data center application in Ireland is 10% of the total production of electricity, which is huge. So 1 megawatt is 10% of a nuclear power plant. It is 30 wind turbine. It is 50,000 photovoltaic panels deployed, actually, which is a huge amount of power, and which is amazing. Actually, in our full report, if you consult it, we did a forecast for the total power consumption, and we realized that the power consumption could be even higher if we didn't optimize the power consumption of servers and reduce losses and power converter and cooling and UPS or so on. So thanks to Eric, which has introduced the drivers of data center. Now, and we know the multitude of drivers and application goes, so all the stuffs, AI, 5G, home office, etc. And now we can understand better the pressure to take into consideration the environmental requirements, such as CO2 reduction, reducing of energy consumption, even reducing the footprint of the data center. So that will make data center enter in a virtuous cycle as following. So, okay, to meet these environmental requirements, as a customer, we have to rethink and rebuild our specification, such as increasing efficiency, reliability, power density, which will force the PSU makers toward the new trends, such as adopting high voltage, high power, higher switching frequency, to end up with all aforementioned requirements. Okay, so to locate what we are talking about, I drew this schematic to show where is the PSU and the powertrain. So starting from the medium voltage from the utility, step down to 400 volt into AC. We have the MV LV transformer. Then we must have a UPS to maintain the power in case of outage. And then we have the PSU, which convert actually the DC voltage or the AC voltage, sorry, from 220 volt to 12 or 48 volt DC. So we are focused on this PSU part and the following. and to discuss about the losses and trends and so on. So again, the key message in this slide is to show the effective power used by the IT. So as you can imagine, we show the results here. So 50%, only 50% are consumed at the end on the power IT, because we have losses in transformers, in UPS, in lighting, and transmission lines, and cooling, and PSU as well. So just keep in mind 30% of cooling, which is the most important part, and the PSU of 6%. So for each level, we can improve the power losses and to save a bit of percentage of the total amount of power. And if we do optimize the overall chain, we can reach 80% instead of 50%, which is something huge. Okay, so now we are going to talk about the PSU technology trends, as I described. I mentioned just the environment requirements. I put here as an example the European standards, which become harder, let's say. So we are taking this last up from 1st January 2023, the efficiency must be 96% instead of 94% of at 50% load. So as we just said in last slides about improvement, we are going from 6% of losses to 4% of losses. So how this can be achieved? So to answer this question, I try to summarize all the technology trends happening at the PSU level, but also at the infrastructure level. So this is the really takeaway slide. We can see all the trends at all levels. We can see the power increasing of the PSU from 1 to 3 kilowatt up to 6 kilowatt. The power density is increasing from 45 watt per inch cube to 100 watt per inch cube. The output voltage is going from 12 volt to 48. The materials of the power switches are tending from silicium to silicon carbide and gallium nitride. The technology trends and infrastructures are as the following. So we are moving from embedded PSU towards separated one. We are for some hyperscale data center, we are replacing the UPS by the BBU, which is the battery backup unit. And of course, we are moving toward from air cooling to liquid cooling. In this slide, we can see this comparison between a standard server and the AI server. So this slide is very important because we can see that for a commercialized AI server, it could consume up to 10 times more than the standard server. We are going to increase the footprint of the server, so from 1 or 2U up to 4 and 5U. We are integrating a GPU and a DPU and only one server, so it's a huge power to consume. And behind we should have the power converter which can handle all this power. So how to do that? So we are, as I said, we are moving from 15 kilowatt rack to 50 kilowatt rack. So the power as the power shelf, we are moving from 15 to 50. And for each PSU, we are moving from 3 kilowatt to 6 kilowatt. So to increase the power of the PSU without losses of the power, we have to use higher voltage, output voltage, so from 12 volt to 48 volt. In this case, we are gonna to reduce by 16 the power losses in the bus bar, as you know, so I square R. And we are going to use silicon carbide and gallium nitride devices, which I let the mic to my colleague Taha to explain you more about this penetration of wide bandgap materials.
Thank you, Hassan. Yeah, so indeed, as you said, so SiC and GaN as a wide bandgap material are being getting more and more attention into the use of the power supply for data centers. As you can see from this slide already, the positioning of GaN and SiC in their usage of the power supply, and yes, they are making more sense to be used in the what we call high power power supply, like with power more than 3 kilowatts and some part of the 1 to 3 kilowatts. So those power supply are mostly used in the for computing servers for hypercycle and HPC. It's where we are seeing the demand for power is increasing, and now we are also hearing about 5 kilowatt power supply being developed by SiC or GaN. As probably I can give you a little bit more of context. So SiC is already used for automotive business, where high power, high temperature operation is required, and there SiC is doing great. And GaN is having a success story for consumer power supply, owing to the high switching speed operation and allowing compactness and small form factor for power supply. And it's getting upgraded toward high power, as you can see, for from hundreds of watts or less than 100 watt consumer power supply now is getting upgraded to few kilowatts power supply. Yeah, so from this slide, you can already see the number of adoption of the wide bandgap, especially the GaN. The SiC, what we have seen that the adoption of SiC is going more silently, as explained in the previous slide, that SiC is more adopted for automotive. So the noise is more made there for automotive adoption and in the powertrain application. But we have the feedback that SiC is already used for power supply units, but without making any advancement. It's not the case for GaN. So the GaN, we hear a lot of noise about adoption of GaN for power supply unit. As you can see, it has already started back in 2020, 2021 with Transform. So Transform is one of the leader supplier of GaN device, who is working with Bell Power Supply. And you can see already they have a suite of power supply unit made by GaN with the power ranging from 1 to 1.5 to 2.5 kilowatts. Other power supply maker are Delta. So Delta is one of the leader supplying power supply, and Delta is working with Infineon. They have already demonstrated 3 kilowatt power supply. And even 4 kilowatt in PCM last year, they demonstrated 4 kilowatt power supply. And one of the also players is actively working on GaN-based power supply unit for data center. It's GaN System, which is now, we can say it's Infineon, as the acquisition of GaN System by Infineon is already completed. So GaN System has been working on the power supply unit for data center since years now, and they demonstrated the highest power density as of today, which is 100 watt per inch cube, with work done by X-Fusion. And a lot of other power supply unit maker are already also getting on board. Like I can mention Liteon, which is also one of the leader supplier of power supply units. And they announced working with Texas Instruments to develop a portfolio of power supply unit made by GaN. So with all of that, like design wins and getting more attention, we expect like GaN and SiC to gain more share in this market, and that's what I will give the mic again to my colleague Hassan to give you more insight about the market and the share of the wide band gap in the power device market for the power supply unit.
So thanks, Taha. So just before going to the supply chain and market, we have the trends about the infrastructure. So I mentioned here two main trends, which is the moving of the PSU from the inside of the server to the outside. So we can see in both architectures, we are moving to the PSU take a dedicated power shelf. Actually, in this way, we can put higher power capacity. We can to respond actually to these power need. We also have this power sharing in the DC buses. We have several advantages to make it external external power supply. Sorry. One of these advantages is the redundancy, because even if the power supply has dropped, we can use the another one, something which is more constrained when the power supply unit is integrated inside the server, because in this case we should have 2N redundancy, which means for each server we should have 2 PSU integrated at the same level. But at the other side of the separated one, we can have N+1 redundancy. So we can save a lot of space and money at the end. But for cooling, so this slide just gives an overview about the current solution existing now. So air cooling and liquid cooling. So obviously air cooling is the mainstream technology used right now, but we are moving towards liquid cooling. Air cooling will stay the simplest way to do so. It will be the mainstream for the enterprise scale. However, liquid cooling could improve as we mentioned earlier, the efficiency from 30% up to 8% of power losses reduction. So that's why there are a lot of investigation done by HPC and hyperscale to deploy the liquid cooling. And again, in liquid cooling, we have direct-to-chip cooling, but also there is a immersion cooling, which is something, let's say, breakthrough technology right now. And the only objective is to increase the efficiency at the maximum point. So now we are moving to the supply chain. We can see the landscape of the power supply unit from the power device suppliers, power devices or passive components, the PSU makers, the power managements, such as UPS, PDU, rack cooling, and the service provider. So the key message of this slide is that we have some of these suppliers, which is repeated in several columns. That means that they have this vertical integration, such as Murata, which have passive components and PSU makers. So those are the main players in the PSU market. The next slide is showing that the most of players are either in Asia or in US. There is no major European player which has been identified by our research. Last one is actually it's a snapshot of a teardown has been done with YOL System Plus, part of YOL Group. This is a power supply unit dismantled and studied component by component by ourselves to understand what are the mainstream topology used, what are the devices from which company they are supplied. So this is a Bell power supply unit. And we also did the breakdown by weight. We can see that the power part is taking 45% of the total. The EMI is taking around 20%, and the cooling and the housing is taking over 33%. So just a hint, if we can improve the cooling, so that means that we could reduce somehow this 33% of the overall. This is our last section on this power electronics chapter for data center. We are showing the market of the power supply unit for 3 categories, which is less than 1 kilowatt, between 1 and 3 kilowatt, and more than 3 kilowatt. Obviously, we can see that the more than 3 kilowatt is taking over the years. This is the part which become more and more present in the market, because as we discussed, there is a big demand for higher and higher power converters. And and accordingly, the device market for the data center PSU increasing. So most revenues are coming from silicon MOSFET devices, but as Taha said, there's some part of the GaN devices, which is in red in this curve, which taking actually a part, especially from the next year and over. So thanks everybody. This was the end of our power electronics chapter for data centers.
So Hassan, thank you so much for this overview of the PSU adoption and the change in data center. And interesting to see that there is a greater adoption on a wide bandgap material in data center. So this comes to the end of the webinar. So thank you to you all. That will conclude our event. As you have seen, there are significant technical advancements in data center. And every slide you have seen today has been sourced from several of reports at Your Intelligence. We sincerely hope this webcast has provided valuable insight to you. And feel free to reach out if you need assistance or have any question on this topic or another. Here are the contacts you can reach out for specific needs. And thank you again for joining us today, and until next time.
Okay, thank you, Eric, and thank you all for listening. Thank you to the speakers for the insightful presentation we have today. Tomorrow, you will find the replay and the presentation on our website. Don't hesitate to have a look at it. Next month, we will present you our last Analyst Thursday webinar of the year in 2023. It will be focusing on China with a different approach to explore the latest insight we have. The webinar is now ending. Thank you all for your attendance, and see you soon.